You want me to go over assignment two with you?
No need.
No need, you know how to do it, okay? Okay, chapter 20. We are going into the sixth topic, modern physics. Uh, Topic 22 is quantum physics. 23 is nuclear physics. Right? What are we going to cover? Energy and momentum of a photon, photoelectricity, wave particle duality, energy levels in atom. Under nuclear physics, nuclear binding energy, radioactive decay. Right? Page 222. Right? There's a syllabus. This one we have taught you already in the previous topic under magnetism, right? Electron volt. This is the only thing that is new Okay, quantum physics 22.1, energy and momentum of a photon, right? There's energy of photon, there's momentum of a photon, c is the speed of light. Then 22.2, photoelectric emission of electron, wave particle duality, energy level in atoms and line spectra. Okay, we are going into a new model if you like. So the particulate nature of electromagnetism, we study electromagnetism as waves. Now we study as particle. Right? Photoelectric emission gives us evidence of particulate nature of electromagnetism. Threshold, we are going to cover threshold frequency, photon energy, work function, and this is Einstein's equation. Then we are going to cover E is independent on I is intensity, E is energy of photon, and then photoelectric current is directly proportional to intensity. Under wave particle duality, we are going to cover electron diffraction, evidence for wave nature, and the Brody wavelength. Under energy levels in atoms and line spectra, we are going to look at hydrogen spectra, especially know how to use this formula, distinguish between emission and absorption spectra. Used to be production of X-ray, used to be this topic used to be 25.6, but now it's changed to medical physics since 222. Speed of light, know where to find it. Planck constant, we'll be using it. And then radioactivity, right? Activity formula or exponential formula, decay constant, right? Know what is given. Okay, let's go to roughly origin of quantum mechanics. Right, so far we have studied about wave. For wave, intensity is proportional to frequency square, inversely proportional 1 over lambda square. Right, that was before 1700. And then the Great Plague of London in 1665. So you can see, look, people start to avoid London, no? Kill 75,000 to 100,000 people. So all those physics before 1800 is called classical physics or Newtonian physics. where we are involved with small velocity compared to the speed of light and large distance, right? Vehicle moving, large object. Modern physics about 20th century lah, after 1900 lah. Right? Here, 2025, this relate to large velocity lah, close to the speed of light, and then small distance. Small distance, we are involved with atomic distance lah. Speed near to speed of light. Distance is 10 to the power minus 9 meter lah. Kinetic theory, right? We have volume of container, pressure of gas in container, absolute temperature of gas, and its number of molecules of gas. M is mass of gas molecule. So together is the total mass, N times M. So P, V, P, and T are called macroscopic properties. It's something we can feel and we can measure. Then we have a formula PV equals to nRT or nKT. We have equation of state. We try to relate temperature to kinetic energy of a gas molecule. We imagine molecules like tiny billiard balls. Particle collide. Particle has a mass and speed and thus kinetic energy. Finally, we relate kinetic energy to absolute temperature. That's why we study about kinetic theory. Right? These are the formulas. Right? We treat our atoms and molecules as particles. Then under waves, so far we have studied waves and its characteristic as interference and diffraction. We think of electromagnetic radiation as waves, thus has a frequency. Modern physics, certain phenomenon or observations cannot be explained by wave nature of electromagnetic radiation. Example, photoelectric emission, right, where the electromagnetic waves fall on the metal surface, electron is emitted. That's called photoelectric emission. If you study today, an electron occupy energy level. Right? Classical physics, waves nature cannot explain all this. Right? Where electron move from one energy level to another energy level, lower energy level, electromagnetic radiation is emitted. The name coined by Max Planck derives from observation that some physical quantities can be changed only by discrete amount. Or sometimes we call it quanta as multiple of Planck's constant, rather than being capable of varying continuously or by arbitrary amount. Right? Just like water, we can boil it at different temperature. We can boil it and we can see temperature rise. That's continuous, but we come to something discrete related to Planck's constant. Okay. Right? This new physics, because we cannot explain some of the phenomenon observations, that's why we introduced new physics, new model, quantum physics. Energy of photon, right? Detecting charged particles. This is your Geiger-Müller counter. This is your counter. This is your Geiger-Müller tube. Geiger-Müller counter can be used to detect both alpha and beta particles. Right? Alpha and beta are particles. So Geiger-Müller can detect their presence. We can either use a loudspeaker, we detect it, and then we can, instead of counter, we can use a loudspeaker that make noise, click, 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 click. Every time there's alpha or beta detected, when a particle is detected, or use a counter which gives the count per second. This is your count per second. That's the counter. It can be used to detect gamma rays. Gamma rays are electromagnetic radiation, that's waves. Right? So gamma rays must behave as particle. If it's going to be detected as radiation, gamma rays can behave as particle. Photon, right? That's our symbol of photon. Right? It has a wavelength lambda. Photon, what is it? Packet or quantum of energy of electromagnetic radiation. Right? Can either think it as a packet or quantum of energy of electromagnetic radiation. Energy of electromagnetic radiation is confined to small individual packets of photons, each of energy. So it is in a packet, and energy is given by H times F. H is called Planck's constant, right? It's got given in the data sheet. This is value very small. And then this is the frequency of the photon, frequency of the wave, photon. You are required to recall and use this formula. Okay, calculate using this formula. See whether you can get the answer. Red light has a wavelength of 700 nanometer. Calculate the energy in electron volt of the photon in the red light. Okay, use this formula only. This formula. Are you familiar with using the formula? And then convert your wavelength to frequency using speed of light equals to F times lambda. Okay. F is C over lambda. H equals to H, E equals to HF. Replace the F with C over lambda. Right? H is given. C is the speed of light. 700 nanometer, convert it to SI unit meter, and that is in joule. So that one you need to memorize. Right? Electron volt is the same magnitude as an electron, charge of electron, right? By in joule. And then 1 joule is one invert of 1.6 of 10 to the power minus 13 joule. Can get the answer? Speak a bit louder, cannot hear.
Okay.
Okay, okay, this is the only thing new. Momentum of a photon. In special relativity, there is an expression relating energy of a particle to its momentum and mass. Don't have to worry about this formula. It's just introduced to let you see the background. For a photon, which has zero mass, a photon doesn't have a mass, the expression becomes mass is zero. So the energy of photon becomes E equals to P0. C is the speed of light. Or another way of saying is a photon has momentum, and the momentum is given by, right? P is for momentum, energy of a photon divided by speed of light. Okay, let's go to look at the video on photoelectricity. What is happening?
Hello, teacher, are you screen sharing?
Wait,
Oh yeah, you are. Can see.
can see the screen?
Can see.
Okay. What is happening? What is happening? Cannot see, let me know, huh?
Mm.
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides with a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction. Now, let me show you that again. I've got a perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on. And it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
Okay, let's carry on with our physics. Let me get my... Okay, with the time we can try to see the others. You want interested? Page 223. That's the syllabus. Recall and use this formula. Okay. Both wave Wave and particle. Both interference and diffraction are properties of waves. Photoelectric effect and the production of X-ray show the particle or particulate nature of electromagnetic radiation. What is photoelectric effect? Photoelectric effect is the emission of electron from metal surface. The key is metal surface. When illuminated, you shine the light on the by electromagnetic radiation of certain energy, not all energy, certain energy. That means certain frequency will cause emission. As you have seen, visible light doesn't cause emission on zinc plate. Right? Sometimes people use irradiated, means the same thing. You shine the light on the metal surface. Right? This is the illustration, electromagnetic radiation, EMR. Right? Shine surface, electrons emitted. Right? Conductors, example metal, they have free electron. Right? Conductors have free, or we call it delocalized electron. Free in a sense it can move within the metal. Electrons are not tightly bound to any particular atom, but are bound to metal ions as a whole. It's bound to the metal ions. What happens if we try to escape outside? They are free to move within the metal. Yeah, they are free to move within the metal. They are slowed down by the positive ion. As any electron moves towards the surface of metal, is retarded by a resultant attractive force from neighboring positive ions. Right? All the positive ions will try to decelerate it, so there's a resultant attractive force, prevent it from escaping. The electron slows to a stop before reaching the surface, before it escapes. An electron in metal does not have sufficient kinetic energy to escape. So electron in the metal doesn't have enough kinetic energy to escape. To escape, electron need a minimum energy. This minimum energy we call work function from an external source. Example, electromagnetic radiation. Right? This picture is just to illustrate to you this electron trying to escape. Right? It's attracted by this positive ion. Remember, it's 3 dimension. Positive ion. Right? Show you the forces acting on the electron. So there's a resultant force retarding it, the green arrow. So what is work function? Minimum energy of photon or minimum energy of electromagnetic radiation to cause emission of electron from the surface of metal with zero kinetic energy. Right? That's the work function. The minimum energy for it to escape the surface with zero kinetic energy. Same work function F H times F naught. F naught is the threshold frequency. It means the frequency. What is the threshold frequency F naught? Same minimum frequency of electromagnetic radiation for electron to emit from the surface of metal with zero velocity. Right? That's the threshold frequency is the minimum frequency of electromagnetic radiation for electron to be emitted from the surface of metal with zero velocity. Okay, try to calculate for me 1.9 electron volt in joule. See whether you can get the answer or not. Right? Different metal have different work function. Cesium have 1.9 electron volt, beryllium 3.9 electron volt. So 1.9 electron volt, what is it? Convert to joule. Can you get the answer?
1.9
1.9 electron volt, convert it to joule.
3.04.
This one you need to memorize. Right? 1.9 times 1.6 and 10 to the power 19. 3.0 times 10 to the power minus 19 joule. Okay? Any comment? Where did you
Yeah,
go?
okay.
Right? Make sure you know how to convert from electron volt. Okay.
Yeah, I said 3.04.
Okay. We got 10 more minutes. Right? Potential well and work function. You can imagine. Yeah. Any problem? Okay.
Yeah.
Okay. That is your electromagnetic radiation. Violet, quantum. That's your electron at the bottom. The potential well. The potential well, we can think of it like work function. Work function is like potential well. Electron is at the bottom there. So you must need this energy to escape. So if the energy is provided by electromagnetic radiation, right, like this blue line, more than the work function, then it will the rest of the energy will escape as electron energy. Right? Compare electron with a person in the bottom of a well with totally smooth sides. The person can only get out of the well by one jump. They cannot jump halfway up and then jump again. Electron at the bottom of potential well must be given enough energy to escape in one jump. The energy is the work function for the material. High energy violet quantum energy of photon greater than work function, and electron leaves metal with kinetic energy. Right? We come to Einstein's photoelectric equation. EK is HF minus phi. Right? There's another way to represent it. Electron is in the bottom of the potential well. This energy. These are electrons, trapped electrons. These are minimum energy required to escape. That minimum energy will function. When a photon meets an electron, the photon gives all its energy to the electron. It cannot give part of it only. It gives completely or none at all. If energy is not enough, it will just pass through. That's the energy of the photon. So by conservation of energy, photon energy equals to maximum kinetic energy of emitted electron plus work function. That's work function. Electron emitted with a maximum kinetic energy, EK max. That's the kinetic energy of the electron. That's the maximum kinetic energy of emitted electron. This incident photon. The photon is the one that gives the energy to the electron. This work function. Due to the attractive force of the metal, attractive force of the positive ion on the electron. Different metal have different work function. So when a photon of energy, that's a photon, greater than the work energy equal to or greater than the work function falls on the surface of metal, is absorbed. Part of the photon energy given to the work function. The rest appear as maximum kinetic energy of the emitted electron. This is a statement of conservation of energy. Where the photon energy equals work function, electron leave with zero kinetic energy. That's all. You can visualize what is happening. Analogy to visualize what happened to electron in metal and photons. You can think of a big hall, which is the metal. Student running at random, which are free electrons. And then photon, these are students standing on the stage and throwing balls at random. Okay? So these students are, the ball are the photons. Not all the ball will hit the student. That you must remember because it's random. It's not aiming. When the ball hits the student, it gives all its energy and disappears. That is nothing different. Right? From the analogy, the ball hits the student, the photon hits the electron, it gives all the energy to the electron. Not all photons will meet an electron, as both are relatively small. Okay? Particle, photon as particle, electron as particle, they are relatively small. When a photon collides with an electron, it transfers all its energy to the electron. Transfer energy is instantaneous, straight away. Okay? No time lag, no delay. The photon gives all its energy to the electron and disappears. Right? So when the photon meets an electron, if energy is sufficient to overcome the work function, then we give the energy completely to the electron. But if it's not sufficient, it will just pass through. It won't give the energy at all. If the energy of the photon is not enough, the electron will not receive it. Unlikely electron will receive two photons to escape because we are both are very small. Right? Cannot receive one, not enough, and then another one, not enough. Add the two together and then escape. Unlikely. Where the energy is just sufficient for the electron to escape with zero kinetic energy, then the work function equals to threshold frequency times Planck's constant. For electron to escape, the photon must have energy equal or greater to the work function of the metal. When the energy of photon is greater than the work function of the metal, the electron is emitted with maximum kinetic energy. It's unlikely the electron will meet two photons at the same time. We are just repeating. Photon and electromagnetic radiation incident on metal. That's a photon. Usually we draw it this way. Photon coming in or incident may not encounter any electron pass through the metal. It doesn't encounter electron, it will pass through. Encounter electron, can you accept my energy or to escape? Not for sufficient energy, photon pass through. No emission. Photon coming in, can you accept my energy? Sufficient energy. Photon gives all energy to electron and disappear. Right? We are just repeating. So electron is emitted. Look at the equation. We write the equation, kinetic energy against frequency. Ek max of electrons when photons with different frequency falls on the metal surface. Right? H and phi or work function are constant. Compare with equation of straight line. Right? This is the equation of a straight line. Frequency can compare to x, Ek max compared to y. So gradient is your Planck constant. Y-intercept is a work function minus work function. When y equals 0, which is this line, y equals 0, right? The x-intercept is the threshold frequency, this f0, this minus work function. Sketch on the same graph for the metal of higher work function. So how would the graph look like for metal of higher work function? Yep. That's the original graph. Where would the graph be? How would it be? A curve, a straight line above or below? Yep.
Higher work function above?
Work function, it should be below.
No, I didn't. No? Yeah.
Gradient give Planck constants, it should be a straight line below. Okay or not? Yep. Gradient is
Oh, okay.
constant, so it's still a straight line. Greater y function means greater y-intercept. Lor. Anytime it will stop, then you can try the worksheet lor, while you wait for 15 minutes break. Okay. Why are electrons emitted with a range of velocity? Can